Okay, so we're moving on to talk now about not just geometric series, but infinite geometric series. Remember this symbol down here, oop, that was in red, this symbol down here represents infinity. So, some geometric series have an infinite number of members. Depending on the value of the common ratio r, some of these series can be found while others cannot. Now if you look at this particular infinite series, which means it just keeps adding and adding and adding, you figure out pretty quickly that adding up terms that your sum is going to grow bigger and bigger and bigger and bigger. This series sum cannot be found because it keeps adding larger and larger numbers. The series blows up towards infinity. Let's figure out what the ratio, the common ratio is for these sets of numbers. If you look at it, it's going to be 8 divided by 4, which is 2. So for a common ratio of 2, you're going to get a series that blows up to infinity when you try to add up all the terms. Now in this particular case, we can get a solution or a sum because the numbers they get consecutively smaller and smaller and smaller. So this series will actually approach a finite sum. We'll have an exact value as it approaches, as the number of terms approaches infinity. If we look at this one, you think about the sums here, they're going to get smaller and smaller. We can figure out the common ratio. So 1 over 8 divided by 1 over 4 multiplied by the reciprocal, and you'll get r equals 1/2. So for this particular case, the common ratio is 1/2. So it's worth noting that the absolute value of r is less than 1 in this case, and in this case we do get an actual sum. So here's a graphical depiction of that series we just talked about, 1/2 plus 1/4. If we look at each of the terms, you can see that for each term the value gets successively closer to 1. Now if you look at the first term, you get 0.5, the second one you're going to get 0.5 plus 0.25 is 0.75, then you add 1/8, then you're going to get 8.875, etc. So these numbers are going to get closer and closer. So the first sum is there, sum 3 is up here, and then the seventh sum is getting really close to 1.0. If you work out to infinity, you're eventually going to reach 1.0 for that sum. So we have a new formula. The sum S of an infinite geometric series, where r is between -1 and 1, is given by S equals a sub 1, that's the first term, divided by 1 minus r, the common ratio. Now notice we don't have an S sub n here. It's an implied S sub infinity. So that's what this equation is implying. So this is the sum for an infinite geometric series. And I want you to think about how that looks somewhat like this formula, which we used for a finite geometric series. But let's think about what happens to this equation when n approaches infinity. So when n gets really, really big. So if you think about it, let's say the r was 1/2, for example. And then you're going to raise it to some really big number. So I said 785. That's just a randomly big number. But the point is, when you raise 1/2 to a really big number, that number gets really, really small. So it's going to be 0.000000, a whole bunch of zeros, and then a 1. And 1 minus 0.0000000001 is approximately 1. So what you figure out is that this term will go to 0 as that n value approaches infinity. And that's why this expression, the equation over here on the left, is an expression of the one on the right when two things have to be true. When n goes to infinity and when r is a fractional value, it's between 0 and 1, because that's what makes it go away. Okay, so let's now evaluate the sum of this series, knowing our formula. We said the sum is a sub 1 over 1 minus r. A sub 1 is 1/2, that's our first term. R, we got to figure out what that value is. R is, you take one term divided by the other, and so we're going to get 1/4 divided by 1/2. And we remember that we want to divide, we have a fraction over a fraction, you just multiply by the reciprocal of the denominator. So 1/4 times 2 over 1 is the same as 2/4, which is 1/2. So R is 1/2. Now we can plug that into our formula for the sum of our infinite series, and we'll get 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is just 1. And that's exactly what we saw in the slide before. So, not all infinite series, geometric series, do converge. If R, the common ratio, is greater than 1, then the series is not going to have a sum because it's going to get bigger and bigger and bigger. And you can find that out pretty quickly as you start to add terms. It just blows up. So, we have a couple example, or here's an example problem. Find the sum of each series if it exists. Okay, so the first thing you want to figure out is, does it exist? And the way you do is you check to see what R, the common ratio, is. So let's look at R for part A. First of all, that number was wrong, so I changed it to a 36. It was a little typo. Okay, so here's R. R is going to be 36 divided by negative 12, which is negative 3. And since R is greater than 1, or the absolute value of R is greater than 1, it is not going to have an infinite sum. So you can't find the sum of that series. It's going to blow up. It's going to get bigger and bigger and bigger. Now let's take a look at the second one, part B. Again, we need to find R. R is going to be 3/4 divided by negative 3/2. Again, we multiply by the reciprocal, which is negative 2/3. We can cancel out the 3's, and you're going to get negative 2/4, which is negative 1/2. So that will have a sum. You want to figure out what the sum is. Well, a sub 1 divided by 1 minus r, which is, a sub 1 is 3, that's your first term, over 1 minus r. R is negative 1/2. 1 minus a negative 1/2 is actually 3/2 though, so again, we multiply by the reciprocal, and you're going to get 2. 3 times 2/3 is going to be 2. So that's your sum for the second part. Okay, so now we're going to look at an infinite series in sigma notation. Now notice when we have sigma notation that we have a summation that goes from n equals 1 up to n equals infinity. So that's what's different. It's not going to like n to from 1 to 12 or from 1 to 6. It's going to infinity. So again, the question is, what is your r value and what is your a sub 1 value, and then you can find your sum. So to find a1, now this is general rule, if you don't recognize, like I can look at this and I know that 5 is a sub 1. But if you don't remember that, all you have to do is plug in n equals 1 into your equation to find the first value. So when I set n equals 1 into this little expression, I'm going to get a1 is 5 times 1/2, and n is 1. So 1 minus 1 is 0. So 1/2 raised to the 0 power is just 1. So a1 is 5 times 1, which is 5. Now I need to find r. Well, I've done enough of these to know that since r, this value right here, is what's being multiplied consecutively, so I go times 1/2 times another 1/2 times 1/2 squared times 1/2 cubed, etc. 1/2 is my multiplier. It is my common ratio. So r is 1/2. I have a sub 1. Now I can write my sum of my infinite series, which is a1 over 1 minus r, which is 5 over 1 minus 1/2, which is 5 over 1/2, which is 10. And that's it. So that was pretty straightforward. The trick is to being able to identify what your a sub 1 is and what your r is, and just getting comfortable and familiar with the sigma notation geometric series. Okay, last type of example. This is kind of an interesting one. Repeating decimals may be seen as the sum of an infinite geometric series. So we can write 0.25 repeating as a fraction. And let's give it a try. 0.25252525 would be a short-term expression for the decimal we've been given. And we can rewrite 0.25252525 as a series of fractional additions. So that's the same as 25 over 100, and that would represent the first two terms. So we'll take that, but we also want to do the next two terms, the next 0.225, and so that would be plus 25 over, well now we're going to have two more zeros, so 4 zeros, and so that will be the next term. And then we want to add the next, which is I can add 2 more zeros, so a total of 6 zeros, etc. And you could keep on adding those up, and you'll get an infinite geometric series. which represents your repeating decimal. So, how can we now evaluate or sum up this geometric series? What we need to do is figure out what a sub 1 is and figure out what r is. So a sub 1 is our first term, which is 25 100ths, which is the same as 1/4. Now r is what do we multiply the first term by to get to the second term? And since we're getting 2 more zeros in the denominator, we're multiplying the first term by 1 over 2 zeros, which is 1 over 100. Okay, so r is 1 over 100. Now I can write my equation for the summation. Summation is going to be 1/4 over 1 minus r, which is 1 minus 1/100th. And 1 is 100 100ths, so I'm going to take away 1 and get 99. So I can write as 99 100ths. And then I'm just going to multiply by the reciprocal and get 100 over 4 times 99. But I can simplify that because 100 divided by 4 is 25, so I get 25 over 99. And that is a fractional representation of our repeating decimal 0.25252525. And that's it. Good luck with your homework.